So let me ask you a question so simple that it almost sounds childish. Why is the night sky dark? Most people think the answer is obvious. They say the sun has gone down. The earth has turned away from the sun and we are standing on the shadowed side of the planet. That sounds reasonable. But that explanation only tells us why it is not daytime. It does not explain why the sky itself is black. Because think about what the universe actually is. It is filled with stars. There are hundreds of billions of galaxies, and each galaxy contains hundreds of billions of stars. They exist in every direction we look. Now imagine this idea very carefully. If the universe stretches endlessly and if stars are scattered everywhere through space, then when you look at any point in the sky, your line of sight should eventually hit the surface of a star. Every direction should end in light. The entire sky should look like a continuous sheet of blazing stars. It should glow with the brightness of the sun itself. And yet when you step outside at night, what do you see? You see darkness. You see only a few tiny points of light scattered across a vast black sky. So the real mystery is not why the sun disappears. The real mystery is why the universe itself is not lighting up the night. For hundreds of years, astronomers believed something very simple about the universe. The idea seemed reasonable and elegant. It was built on two assumptions that almost everyone accepted without question. The first assumption was that the universe is infinite. It stretches forever in every direction. There is no edge. There is no wall. If you travel far enough in any direction, you will always find more space, more stars, more galaxies. The universe simply continues without end. The second assumption was that the stars are spread through this infinite space in a roughly uniform way. They are not arranged in a single cluster or gathered in one corner of the cosmos. Instead, they are scattered throughout the universe in all directions. Some regions contain galaxies and some regions contain empty space, but when you step back far enough, the overall distribution looks roughly the same everywhere. Astronomers often used a simple image to describe this idea. They said the stars are like raisins in a pudding. If you look closely, you see lumps and uneven patches, but if you zoom out, the raisins appear scattered throughout the dessert in a fairly even way. Now, these two assumptions seem harmless. An infinite universe and stars distributed everywhere. But when you combine them, something strange begins to appear, something that turns into a logical trap. To understand it, we need a simple thought experiment. Imagine you are standing in the middle of a very dense forest. Trees surround you in every direction. When you look straight ahead, your eyes eventually hit the trunk of a tree. If the forest is small, you might be able to see gaps between the trunks. Through those gaps, you can see the open sky beyond the forest. But now imagine that the forest is not small. Imagine it stretches endlessly in every direction. An infinite forest. Now, when you look ahead, your line of sight eventually hits a tree trunk. Move your gaze slightly to the right, and maybe you miss the first tree, but farther away another tree blocks your view. Move your gaze again, and you might miss two trees, but eventually a third tree stands in the way. If the forest truly goes on forever, then every possible line of sight will eventually encounter a tree. There will be no empty gaps. The entire horizon will be filled with wood. Now replace the trees with stars. Each trunk becomes a blazing sphere of nuclear fire, each one shining with enormous brightness. You are standing on Earth and looking out into the universe. Your eyes send a line of sight outward through space. That line passes the moon. It passes the planets. It passes the nearby stars of our galaxy. But if the universe is infinite and stars exist everywhere, then eventually that line must intersect the surface of a star somewhere far away. It might be millions of light years away. It might be billions. But if the universe has no end, then that line cannot travel forever without hitting something luminous. This leads to a shocking conclusion. Every direction you look in the sky should end at the surface of a star. Every tiny point in the sky should shine with starlight. The dark spaces between the stars should not exist at all, because even if the nearest stars are separated by huge distances, there must always be more stars farther behind them, layer after layer after layer stretching outward forever, each distant layer filling the empty gaps left by the closer one. Eventually, every direction becomes blocked by a star. Think about what this means visually. The night sky should not look like scattered pinpoints of light on a black background. Instead, it should look like a continuous glowing surface, like the surface of the sun itself. The entire dome of the sky should be blazing with light. It should be overwhelmingly bright. In fact, if this picture of the universe were correct, the night sky would not merely glow softly, it would shine with incredible intensity. The earth would be bathed in constant radiation from every direction. The darkness of night would never exist. But when we step outside at night, we see something completely different. We see a sky dominated by darkness. A few stars sparkle across the black background, but the vast majority of the sky is empty and dark. The contradiction between these two ideas creates one of the most famous puzzles in astronomy. If the universe is infinite and filled with stars, then the sky should be bright everywhere. Yet the sky is dark. This simple observation creates a trap for our assumptions. Either the universe is not infinite, or the stars are not distributed the way we imagined, or something deeper about the universe is fundamentally different from what scientists once believed. The darkness above our heads is not just a visual detail. It is a clue. It is evidence that one of our most basic ideas about the universe must be wrong. To see why this logical trap is so powerful, we need to slow down and picture it more clearly. Imagine again that you are standing inside a forest, not a small forest near a town, but a deep forest so thick that trees surround you in every direction. When you look straight ahead, your eyes travel through the air until they strike the trunk of a tree. That trunk blocks your view. Now, move your gaze slightly to the left. You might miss the first tree, but somewhere farther away another tree stands directly in your line of sight. Move your gaze again, and perhaps you miss two trees, but eventually a third tree appears in the distance. The important point is that your eyes are always traveling along straight lines. Your vision extends outward until it encounters something solid. If the forest extends only a few hundred meters, you will eventually see the sky beyond the trees. You will notice patches of blue where your line of sight escapes the forest. Those patches appear because the forest ends somewhere. There is empty space beyond the last row of trees. But now imagine that the forest has no edge. Imagine that it continues endlessly in every direction. No matter how far you walk, the trees never stop. They stretch outward forever. In this infinite forest, something remarkable happens to your view of the horizon. When you look straight ahead, your line of sight hits a tree. When you move slightly to the side, your line of sight eventually hits another tree farther away. Even if you look through a narrow gap between nearby trunks, the forest behind them continues forever. Eventually, another trunk will appear in that gap. Because the forest has no end, every possible direction must eventually encounter wood. There are no permanent openings to the outside world. The horizon becomes a solid wall of tree trunks. You cannot see the sky at all. Now take that image and replace the trees with stars. Instead of dark trunks, imagine brilliant spheres of burning plasma, each one glowing with enormous power. The universe becomes a forest of light. You are standing on Earth, and your eyes are looking out through space. When you choose a direction, your line of sight leaves the surface of the planet and begins traveling through the cosmos. First, it passes the moon and the nearby planets. Then it moves beyond the outer edges of the solar system and enters the sea of stars that fill our galaxy. But if the universe truly stretches forever, and if stars exist everywhere in that vast space, then your line of sight cannot travel indefinitely without encountering one of those stars. Maybe the nearest star in that direction is thousands of light years away, maybe millions. But eventually your line of sight must land on the surface of some distant sun. Now move your gaze slightly to the right. Perhaps you missed that first star, but the universe continues behind it. Farther away, another star waits along that path. Move your gaze again, and perhaps the nearest stars do not line up with your sight line, but the layers of stars behind them continue endlessly. Somewhere in that immense depth, another star must eventually appear. If the universe contains an infinite number of stars distributed through infinite space, then this process never fails. Every direction must eventually intersect the glowing surface of a star. Every tiny patch of sky should contain the light of some distant sun. The empty black gaps between the stars should not exist. Those gaps should be filled by stars farther away in the background. Layer after layer of starlight stacked behind one another across unimaginable distances. Picture what the sky would look like if this were true. Instead of scattered points of light on a dark background, the entire sky would appear bright. Every direction would end in the blazing surface of a star. The dome of the night sky would resemble the surface of the sun. Not identical in detail, but similar in brightness. The darkness of space would disappear completely because every line of sight would terminate in a luminous object. The universe would form a continuous wall of starlight surrounding us from every direction. This conclusion does not depend on complicated mathematics. It comes directly from simple geometry and the assumption that the universe extends forever with stars everywhere. If those assumptions are correct, then darkness should be impossible. Yet when we step outside at night, we see something very different. We see a sky dominated by blackness. Only a few stars puncture the darkness like tiny sparks. Vast regions of the sky remain empty and dark. The infinite forest of stars that our logic predicts does not appear in reality. This is where the puzzle becomes unavoidable. Either the universe is not infinite in the way people once imagined, or the stars are not distributed through space the way we assumed. The darkness between the stars is telling us that something about our picture of the cosmos must be wrong. And to understand exactly what went wrong, we must move from simple geometry to a deeper piece of physics. We must ask how the brightness of light actually changes with distance. At this point, many people think they already see the answer. They say the stars that are very far away must be too dim to see. That sounds like common sense. Everyone has experienced how light fades with distance. If you hold a candle close to your face, the flame looks bright and intense. But if you walk away with that same candle, it becomes weaker and weaker until eventually you cannot see it at all. So it seems natural to believe that distant stars simply become too faint to matter. They are there, but their light is too weak to reach our eyes in any meaningful way. Physics even has a precise rule that describes this effect. It is called the inverse square law. This law tells us that the brightness of a light source decreases with the square of the distance. If a star is twice as far away, it does not appear half as bright. It appears 4 times dimmer. If it is 3 times farther away, the brightness falls by a factor of 9. In mathematical language, we say the brightness is proportional to 1 divided by the distance squared. So if you imagine stars scattered throughout an enormous universe, it seems obvious that the distant ones should fade into darkness. Their light should become so weak that it contributes almost nothing to the sky. But this intuition hides a subtle mistake. The mistake appears when we consider not just the brightness of a single star, but the number of stars that exist at greater distances. To understand this, we can build a simple geometric model of the universe. Imagine placing the Earth at the center of a set of enormous spherical shells that surround us like the layers of an onion. Each shell represents a region of space at a certain distance from Earth. Now suppose that stars are distributed evenly throughout space. That means every region of equal volume contains roughly the same number of stars. Start with the first shell at some distance from Earth. Imagine that this shell contains a certain number of stars and that together they send a certain amount of light toward us. Now consider the next shell, which lies twice as far away. According to the inverse square law, each star in this second shell will appear 4 times dimmer because the distance has doubled. That seems like a huge drop in brightness. But now we must ask a second question. How many stars are inside that shell? The answer comes from geometry. The surface area of a sphere grows with the square of its radius. If the radius doubles, the area becomes 4 times larger. That means a shell that is twice as far away from Earth encloses 4 times as much area as the first shell. If stars are distributed evenly through space, this second shell will contain roughly 4 times as many stars as the first one. Now combine these two facts. Each star in the second shell is 4 times dimmer, but there are 4 times as many stars. The extra stars exactly cancel the loss of brightness. 4 times as many sources multiplied by 1/4 of the brightness gives the same total amount of light. The entire shell contributes exactly as much light as the closer shell. This result does not change as we move outward. Imagine a third shell that lies 3 times farther away. Each star is now 9 times dimmer, but the surface area of that shell is 9 times larger, so it contains 9 times as many stars. Again, the two effects cancel perfectly. The same pattern continues for every shell, no matter how far away it is. Each layer of the universe contributes roughly the same amount of light to the sky. Now we reach the crucial step. If the universe is infinite, there are infinitely many of these shells extending outward into space. Each shell adds the same amount of light as the previous one. To calculate the total brightness of the sky, we must add the contribution from the first shell, plus the second shell, plus the third shell, and so on forever. That means we are adding the same number again and again, an infinite number of times. The result of such a sum is not a finite brightness. The result is an infinite amount of light. In reality, stars have size and can block one another, so the brightness would not literally become infinite. But the calculation shows that the sky should approach the maximum possible brightness. Every direction we look should eventually terminate on the glowing surface of a star. The sky should resemble a continuous wall of starlight rather than a dark background dotted with points of light. Yet when we look upward, we see a sky dominated by darkness. The inverse square law that seemed like an obvious escape does not solve the paradox at all. Geometry cancels its effect completely. The distant universe cannot hide simply by being far away. The darkness of the night sky must have a deeper explanation. At this stage, scientists began searching for a simple escape from the paradox. The mathematics seemed solid, but the conclusion was absurd. The sky is clearly dark, so something in our reasoning must be missing. The most natural idea was that the light from distant stars does exist, but it is blocked before it reaches us. Space, after all, is not perfectly empty. It contains clouds of gas and dust drifting between the stars and galaxies. These clouds are made of tiny particles left behind by dying stars and cosmic explosions. So astronomers proposed a simple explanation. Perhaps the universe really is filled with stars stretching out forever. But we cannot see most of them because their light is absorbed by dust. This idea sounds extremely reasonable. We experience something similar every day on Earth. Imagine driving a car through thick fog at night. The headlights of distant vehicles disappear because the fog scatters and absorbs the light. The farther the light travels, the more it is weakened by the mist. Eventually, the light fades completely and the distance beyond the fog becomes invisible. If cosmic dust works the same way, then perhaps the distant stars are hidden behind enormous clouds of material. Their light never reaches our eyes. The darkness of the night sky would simply be the shadow created by this cosmic fog. For a long time, many astronomers believed this explanation solved the problem. It seemed simple and intuitive. But physics has a habit of exposing hidden flaws in simple ideas. The flaw appears when we remember one of the most fundamental principles in all of science. Energy cannot simply disappear. This rule is called the conservation of energy. It tells us that energy can change its form, but it cannot vanish from the universe. Whenever energy seems to be lost, it must have been transformed into something else. Now think carefully about what happens when a photon of starlight strikes a grain of dust. That photon carries energy as it travels through space. If the dust particle absorbs the photon, the light itself may disappear from view, but the energy does not vanish. Instead, the dust particle gains that energy. Its atoms begin to vibrate more vigorously. In other words, the particle heats up. Imagine a tiny grain of dust floating in space. Photons from distant stars strike it from every direction. Each photon deposits a small amount of energy. Over time, the dust grain absorbs more and more radiation from the surrounding universe. As it absorbs this energy, its temperature rises. And here we encounter another basic law of physics. Any object that becomes warm begins to radiate energy again. Warm objects glow. They emit radiation of their own. We see this effect clearly in everyday life. If you place a piece of metal inside a furnace, it starts out dark. As it absorbs heat, it begins to glow red. With more heating, it becomes orange and then white hot. Eventually, it reaches a temperature where the energy it radiates away equals the energy it absorbs from the fire. At that point, the metal reaches equilibrium. It shines steadily with the same intensity as its surrounding. The same thing must happen to dust in space. If the universe were infinite and filled with starlight, the dust clouds would spend billions upon billions of years absorbing radiation. Over such enormous time scales, the dust could not remain dark. It would heat up until it reached a temperature where it radiates as much energy as it absorbs. Once that equilibrium is reached, the dust itself would glow. Now consider what this means for the night sky. Even if dust blocked our view of distant stars, the absorbed energy would eventually be re-emitted as radiation. Instead of seeing a wall of stars, we would see a glowing fog of hot dust filling the sky. The brightness would remain. The energy would simply appear in a different form. Dust cannot permanently hide the light of the universe because it cannot destroy the energy carried by that light. So the dust explanation collapses under the weight of thermodynamics. It cannot solve the paradox. If the universe were truly infinite and had existed forever, the dust would have already reached equilibrium with the radiation around it. The sky would still blaze with light. It might be starlight or glowing dust, but either way the darkness would disappear. This realization forces us into an uncomfortable position. The geometry of the universe predicts a bright sky. The physics of energy conservation confirms that the light cannot simply vanish. Yet the sky above us remains dark. The contradiction is telling us that something deeper in our picture of the universe must be wrong. Either the universe is not infinite in the way we assumed, or it has not existed forever, or something about space itself behaves differently than we imagined. The darkness of the night sky is not a trivial detail. It is a clue that one of our most basic assumptions about the cosmos must be false. And to uncover the real answer, we must examine a completely different possibility. Perhaps the structure of the universe itself is not uniform at all scales. Perhaps the stars are arranged in a more complex pattern than the simple models we have used so far. At this point, you might still feel that there must be some hidden loophole in our reasoning. Perhaps the problem lies in the assumption that stars are spread evenly throughout space. When we look at the real universe, we do not see stars arranged like grains of sand on a beach. We see structure, we see clusters, we see enormous empty regions where almost nothing exists. Our own star sits inside a galaxy. That galaxy is part of a cluster of galaxies. The cluster itself belongs to an even larger structure called a supercluster. Between these structures lie vast cosmic voids where very few galaxies exist. So it is tempting to imagine that the universe is not uniform at all. Perhaps it becomes emptier and emptier as we look farther away. This idea leads to what mathematicians call a fractal distribution. A fractal is a pattern that repeats itself at different scales, but becomes increasingly sparse as the scale grows. You can imagine a branching tree, where each branch splits into smaller branches, and those split again into even smaller ones. The pattern continues, but the empty spaces between the branches grow larger and larger. If the universe were arranged like this, then our earlier calculation would change dramatically. Instead of each spherical shell containing more and more stars in proportion to its surface area, the number of stars might grow more slowly. Perhaps the farther shells contain fewer and fewer stars relative to their size. In that situation, the total light from distant shells might shrink rather than remain constant. Instead of adding the same brightness again and again, we might be adding smaller and smaller contributions. Mathematically, the series could look like 1 plus 1/2 plus 1/4 plus 1/8 and so on. A sequence like that does not explode to infinity. It converges to a finite value. If the universe were truly fractal in this way, the night sky could remain dark because the vast majority of space would be almost empty. Only the nearby regions would contain significant numbers of stars. The deeper layers of the universe would contribute less and less light until their effect became negligible. This was not just a speculative thought. About a century ago, the Swedish astronomer Carl Charlier proposed a model of the universe built on exactly this idea. In his picture, the cosmos formed a hierarchy of clusters within clusters. Stars gathered into galaxies, galaxies gathered into clusters, clusters gathered into even larger clusters. At every new level, the distances between structures grew faster than the number of objects. In such a universe, the density of matter would drop as we examine larger and larger scales. The light from distant regions would fade away, not because of dust or dimming, but simply because there were fewer sources of light out there. On paper, this idea works beautifully. The mathematics removes the paradox without violating any physical laws. But physics is not decided by elegant mathematics alone. Nature has the final word. To test the fractal idea, astronomers began mapping the distribution of galaxies across the sky. Over the last several decades, powerful telescopes and large sky surveys have measured the positions of millions of galaxies. These observations allow scientists to construct enormous three-dimensional maps of the universe. What these maps reveal is fascinating. On small and medium scales, the universe does look extremely clumpy. Galaxies form long filaments and sheets that weave through space like a cosmic web. Between these filaments lie enormous voids that contain very few galaxies. If you zoom in on a region a few million light years across, the universe appears chaotic and uneven. But when astronomers examine regions hundreds of millions of light years wide, a surprising pattern emerges. The irregularities begin to smooth out. The density of galaxies becomes roughly the same everywhere. Beyond a certain scale, the universe stops looking fractal. Instead, it behaves like a uniform fluid. No matter where you look, the average number of galaxies within a large enough volume is nearly identical. Cosmologists describe this property with a principle that lies at the foundation of modern cosmology. It is called the cosmological principle. The principle states that on the largest scales, the universe is homogeneous and isotropic. In simple language, it means that the universe looks essentially the same in every direction and from every location when viewed at a sufficiently large scale. This discovery destroys the fractal escape route. Because the large-scale universe is roughly uniform, our earlier shell calculation becomes valid again. The distant layers of space do contain enormous numbers of stars and galaxies. Each layer should contribute roughly the same amount of light. If the universe had existed forever, the sky would indeed be flooded with radiation from those countless sources. So once again, we find ourselves cornered. Dust cannot hide the light. Fractal structure cannot remove it either. Observations tell us that the universe becomes smooth and uniform at large scales. The geometry still demands a bright sky. Yet the night above us remains dark. When every possible escape route collapses, we are forced to reconsider the deepest assumption of all. Perhaps the universe has not existed forever. Perhaps the reason the distant light does not reach us is not because it is hidden or absent, but because it has not had enough time to arrive. At this point, we have eliminated nearly every possible escape. The stars exist, Dust cannot hide their energy. The universe is smooth on large scales, so distant shells should still contain enormous numbers of galaxies. Geometry tells us the sky should glow. Yet the sky is dark. When scientists reach a situation like this, it usually means that one of the deepest assumptions must be wrong. In this case, the assumption hiding in the background is the idea that the universe has existed forever. For centuries, people imagined the universe as an eternal stage. The stars were the actors moving across a cosmic theater that had always been there and would always remain. But what if that assumption is false? What if the stage itself had a beginning? To understand why this possibility changes everything, we need to remember one crucial fact about light. Light does not travel infinitely fast. It has a specific speed. In everyday life, that speed feels instantaneous, but on cosmic scales, it is surprisingly slow. Light travels about 300,000 kilometers every second. That is incredibly fast compared with anything we build on Earth. But it still takes time to cross the vast distances between stars and galaxies. When you look at the moon, you are not seeing it as it is right now. You are seeing it as it was about 1 second ago, because that is how long the light needed to reach your eyes. When you look at the sun, you see it as it was about 8 minutes ago. If the sun vanished at this moment, the Earth would continue receiving sunlight for 8 minutes before the news arrived. Now extend this idea to the entire universe. When we observe distant stars and galaxies, we are actually looking into the past. The farther away an object is, the longer its light has been traveling before reaching us. A galaxy 1 million light years away appears to us as it looked 1 million years ago. A galaxy 1 billion light years away appears as it was 1 billion years in the past. A telescope is not just a magnifying instrument. It is also a time machine that allows us to see earlier chapters of cosmic history. Now combine this idea with a second possibility. Suppose the universe itself has a finite age. Suppose there was a moment when the universe began. Modern measurements show that our universe is about 13.8 billion years old. That number is enormous compared with human history, but it is still a finite amount of time. If light requires time to travel, then there is a limit to how far we can see. Any star or galaxy whose light would require more than 13.8 billion years to reach us simply has not had enough time to send its photons to Earth. This creates a natural boundary around everything we can observe. Imagine drawing a gigantic sphere centered on Earth. The radius of that sphere is determined by the age of the universe multiplied by the speed of light. Inside this sphere lie all the stars and galaxies whose light has had time to reach us since the universe began. Outside that sphere, there may be countless additional stars. The universe may even extend infinitely far beyond it, but their light is still traveling through space. It has not yet arrived. This region is known as the observable universe. It is not a physical wall in space. It is a horizon in time. Beyond that horizon, events exist, but their signals have not yet reached us. From our point of view, they remain invisible. Return now to our earlier image of the infinite forest. Previously, we imagined standing in a forest that stretched forever and had existed forever. In that situation, every line of sight eventually hits a tree trunk and the horizon becomes solid wood. But now imagine a different situation. Suppose the forest appeared only a short time ago and light travels slowly through the trees. When you look around, you can only see the trees that are close enough for their light to reach you since the forest came into existence. The distant trees still exist, but their light has not arrived yet. In that case, you would see gaps between the visible trees. Those gaps would appear as darkness. This is exactly what happens in the universe. When you look at a dark patch of sky, you are not necessarily looking at empty space. You are looking beyond the edge of the visible forest of stars. The deeper layers of the universe may contain many more stars, but the light from those regions is still on its journey toward us. It has not yet had enough time to arrive. This insight solves most of the paradox. The sky is dark not because stars are missing, but because the universe has a beginning and light has a finite speed. The distant universe has not had enough time to fill the sky with starlight. In cosmic terms, the universe is still young. 13.8 billion years sounds immense, but compared with an infinite universe, it is just the opening moment of the story. Yet there is still one more subtle effect that makes the night sky even darker. The universe is not simply aging with time. It is also expanding. Space itself is stretching, and this stretching changes the energy of the light that travels through it. Understanding that final effect will complete the explanation of why the sky above us appears so dark. Now we arrive at the final piece of the puzzle. The finite age of the universe explains most of the darkness in the night sky. The light from extremely distant stars simply has not had enough time to reach us yet. But the universe has one more trick that deepens the darkness even further. The universe is not static. It is expanding. In the early 20th century, the astronomer Edwin Hubble made a discovery that changed our understanding of the cosmos. When he measured the light coming from distant galaxies, he found something remarkable. Almost all of them were moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This observation revealed that the universe itself is expanding. Space is stretching in every direction, and the galaxies are being carried apart by that expansion. To understand why this matters for the brightness of the sky, we need to think about the nature of light. Light behaves as a wave. It has a wavelength and a frequency just like sound. When a sound source moves away from you, the waves become stretched and the pitch drops. This is the familiar Doppler effect that you hear when a passing siren changes tone as it moves away. The same idea applies to light. When a light source moves away, the waves of light become stretched to longer wavelengths. Blue light becomes greener. Green becomes yellow. Yellow becomes red. Astronomers call this effect redshift because the light shifts toward the red end of the spectrum. But in the expanding universe, something even more dramatic happens. The stretching is not caused only by galaxies moving through space. The space itself is stretching while the light travels through it. Imagine drawing a wavy line on a rubber band. That line represents a beam of light. If you pull the rubber band from both ends, the wave on it stretches as well. The peaks move farther apart and the wavelength becomes longer. The same process happens to light traveling through expanding space. As the universe grows larger, the wavelengths of photons are stretched along with it. This stretching has an important consequence. Longer wavelengths carry less energy. A photon that began its journey as bright visible light slowly loses energy as the universe expands. Its wavelength grows longer and longer until it moves beyond the range our eyes can detect. Light that was once visible becomes infrared radiation. If stretched even further, it becomes microwave radiation and eventually radio waves. Our eyes cannot see these forms of light. To us, they appear as darkness, even though the radiation still exists. Now think again about the distant stars that fill the universe. Their light has been traveling toward us for billions of years, while the universe has been expanding the entire time. By the time that light arrives, its wavelength may have stretched so dramatically that it is no longer visible to human eyes. Instead of seeing bright starlight, we receive extremely faint radiation at much longer wavelengths. The expansion of the universe acts like a cosmic dimmer switch that reduces the energy of the light reaching us. This leads to a surprising realization. The sky is not truly dark. It only appears dark because our eyes are sensitive to a very narrow range of wavelengths. If we possessed eyes capable of seeing microwave radiation, the sky would look completely different. Instead of blackness, we would see a faint glow filling every direction. That glow is real, and it has been measured by astronomers. It is called the cosmic microwave background. The cosmic microwave background is the oldest light in the universe. It comes from a time about 380,000 years after the universe began. In those early moments, the universe was extremely hot and dense. Matter existed as a glowing plasma of electrons and protons mixed with intense radiation. Light could not travel freely because it constantly scattered off charged particles. But as the universe expanded, it cooled. Eventually, the electrons and protons combined to form neutral atoms, and the fog of plasma cleared. At that moment, light was finally able to travel freely through space. That ancient radiation has been traveling across the universe ever since. During the billions of years of cosmic expansion, its wavelength has been stretched enormously. What was once brilliant, visible light has been transformed into microwave radiation with wavelengths of a few millimeters. Today, it fills the entire universe like a faint echo of the original fireball of creation. This radiation was discovered in 1964 by two radio astronomers, Arno Penzias and Robert Wilson. While testing a sensitive antenna, they detected a persistent background noise coming from every direction in the sky. At first, they suspected technical problems or even contamination from pigeon droppings in the antenna. But after careful investigation, they realized the signal was real. They had accidentally detected the afterglow of the Big Bang. So the paradox of the dark night sky leads us to a profound truth. The sky appears dark not because the universe is empty, but because the universe has a beginning and because space is expanding. The finite age of the cosmos limits how far light has traveled, and the expansion of space stretches that light into wavelengths invisible to our eyes. The darkness we see is not the absence of radiation. It is the result of cosmic history written across billions of years. There is also a deeper meaning hidden in this darkness. Life itself depends on it. Every living system requires a flow of energy from a hot source to a colder environment. The sun provides us with high energy radiation that powers photosynthesis, drives weather, and fuels the chemistry of life. But for that energy to do useful work, it must eventually be released as lower energy heat into the surrounding universe. The dark, cold sky provides the place where that waste energy can escape. Without the cold darkness of space, there would be no gradient of energy and no processes capable of sustaining life. So when you look up at the night sky and see a vast black background scattered with stars, you are not seeing emptiness. You are seeing the evidence of a universe that began in a fiery birth and has been expanding and cooling ever since. The darkness above us is the silent record of that history and the quiet condition that makes our own existence possible.